Sayın Haluk Güreren'e çok teşekkür ediyoruz ve konferansımızın son konuşmacısı 27 yıllık cephe mühendisliğinde önemli deneyime sahip Glass şirketinin kurucu ortaklarından Tim McFarlane. Kendisi tasarım için buluşlar başlığındaki konuşmasını yapmak adına bizlerle, sunumunu bizlerle paylaşmak adına kendisini sahneye davet ediyorum.
Thank you. Thank you very much. Thank you to the organizers and the sponsors of this event. It's nice for me because it's the second time I've come here to speak, which is quite an honor. I must have said the right thing last time. I don't know. Anyway, it's also interesting to follow two speakers who I think are very relevant to what I'm going to say today. The last speaker from industry, talking about the extraordinary advances that the glass industry has made, particularly over the last 50 years. I think the float line process for making glass brought the cost of glass down to such a level that it became an economic product to use as the total facade for a building, which of course fulfilled the great architect Mies van der Rohe's vision of a world of glass and everything being glass. And I think the speaker before that talked about the other aspect that I'm going to bring into my discussion, which is the architect and the role he plays in bringing ideas into the world, and the importance of bringing ideas into the world. And the reason we have these hero figures in architecture, Mies van der Rohe, Le Corbusier, and many other figures in the 20th century, including our own contemporary architects, they have a role to play to represent our culture, to represent our contemporary culture. And our culture includes technology. Our culture includes how we use technology and how we can use technology. Now, I am an engineer, so what business do I have to stand here to talk about architecture on one hand and industry on the other? Well, the delightful thing is that they need me. They do, honest. When did I learn this? I didn't learn it when I was designing steel and concrete buildings, which is what I did most of my life. I learned it when an architect asked me to design, or to help them design, a glass staircase. Well, like one of the earlier questioners, the idea of a glass staircase did not make sense, because you wouldn't walk in it, you'd be too scared, right? So my natural reaction was, I'm sorry, I can't help you. However, these architects, they can be very persistent. So they said, no, you must help. Oh, so okay, so I thought, well, who knows about glass? Well, the glass industry knows about glass. The glass industry know everything about glass. I'll call them up. So I called up the glass industry and I said, excuse me, how do you make a glass staircase? Oh, they said, you make it with 25 millimeters of float glass in a steel frame. Okay. So I went to the architect and I said, you make it with 25 millimeters of glass in a steel frame. And she, being an architect, said, I don't like the steel frame. So I went back to the glass industry and I said, how can you do it if there's not a steel frame? And they said, you can't. So I said, well, okay, maybe you can tell me, because I'm an engineer, maybe you can tell me how strong glass is. Said the industry, ooh, that's a difficult question. I said, what, a difficult question? Well, it's a difficult question. I know the tensile strength of steel. It's in the book. Tensile strength of concrete, well, compressive strength. It's in a book. Oh, there isn't a book for glass. No book for glass. Oh, okay. So I went back to the architect and I said, really, I don't know the answer. She said, no, very persistent. She said, no, come on, we must find an answer. So I went digging around in the literature and I found this old book, very old book, 1940 old book, even before float glass book. And in it, in this book, there was the number, the tensile strength of glass. It was like finding the Holy Grail, or whatever the equivalent is in Islam, I don't know. And it was just wonderful. But it didn't give any explanation. It just said the tensile strength of glass is 70 MPa, 70 MPa. So I thought, is that when it broke? Or, I didn't really know what to do with this number, really. So I did what every good engineer should do when they don't know very much, which is I divided by 10. Okay? So instead of using 70, I used 7. And I designed my first glass tread. But wait a minute. What happens when it breaks? You're standing on it. Scary. Anyway, that was the beginning of my adventure. And I call it an adventure because it was an adventure, because up until that time my engineering had been a bit boring. Sorry, civil engineer, but try and make your life interesting because it's important. And the way to make your life interesting is to actually have to take responsibility for something. Tricky. It's very nice if you've got a book, it says it in the book. Do it like this. Done it before, there it is. Done it before and then the book is good. That's important. You need it. But what you really need to change the economy, to change the whole aspiration. Okay, the aspiration. What do you want to be? What do you want to do? Where do you want to be in the world? To do that, you've got to take responsibility at a deeper level. I learned this, okay? I learned this. It's not that it was something that I'm making up. This is something which I experienced, and it was a great privilege to experience. And I would never have experienced it had it not been for this curious material called glass. So I started a journey, and I'm going to describe that journey, which goes from 1988 through till now, really. And I want to describe, I'm going to call them inventions, and I'm going to call them more particularly to make them distinct from industrial inventions. Industrial inventions are making float glass, making all those coatings, making the U value better, making everything performance-wise better, or it may take another focus. And industry's a big, big thing. And you're a little architect, please, can you help me? It's difficult. Big industry would like to help small architect, but the risk is enormous because if the small architect's adventurous, wonderful project has a problem, So does the big glass company. So there needs also, as long as we have architects with imagination and ambition, alongside them there needs to be the people who can carry out that work. And that person who was making those architectural projects we saw earlier in the afternoon, the person who was making that, he wasn't a big company. He could afford to take the risk and produce beautiful, handcrafted, wonderful things that fulfill the architecture. And it's so important as an industry, as a country, you know, as humanity, that we actually understand where things can progress and how they can progress. And in the humbler world of what we do, I think it can be represented by encouraging architecture. Not every building can be an opportunity for architecture, we know that, but encouraging it where it can happen, and having an industry and an infrastructure of design consultants who can take responsibility and push things through. Because this is what I discovered in my 25 years of design, working alongside architects, was that the structural engineer can facilitate something happening. Now you say, well, how? Okay, I'll give an example. We did a project in America, and it was a big glass wall, okay? And it had a diameter of 60 meters, so it wasn't a small. The Suleimani Mosque has a diameter of 26.5 or 27.5, depending which book you read. But that's big. Now this was 60 meters, and this is a wall, a glass wall. And we came up with a design with the architects' desire to have it completely transparent. We came up with a design which was at one level very simple, and at another level had never been done before. So we invited the people who could do these things in to talk with us, and they said, yeah, this seems fine, except when it came to doing the tender and the bid. So they bid the project, and then they all came back and said, actually, we can only do this. Now, all three of them came back with a very different answer, and what was also interesting to our client was that the cost of the wall that they were offering was 2.5 times more than we'd estimated our design should cost. So the client said, what am I going to do? You know, this is like $5 million. Huh? I don't want to spend $5 million on this clever design. And we were sort of stuck. Well, why can't they just build it? Now here's where our role is, okay? It's called design responsibility. We took design responsibility from the contractor, from the glass contractor, to us, okay? Small move, but big difference. Because when we did that, then we could find people to build it. What, you take design responsibility? Okay, we'll build it. So you need that, you need the engineers to take responsibility and to spend the time during the design period, which can sometimes be quite long, working it all out, making sure that it works, and then things can move forward. And all of these examples are just examples of that. It moved things forward, sometimes to maybe not great advances, but sometimes to things which have led to becoming standards in the industry. So, now the show. So this is the other stuff that we do, which is a mixture of still very exciting structures, big buildings, timber structures, stadiums, long cable span structures, concrete structures, and the little glass structures here. So the glass structures don't represent the biggest part of our portfolio, but they definitely represent the most exciting in terms of discovery of what it is to have design invention. Now, I just thought I'd pop these in because I'm becoming more and more familiar with Istanbul as time goes on, and it started really with a long time ago, a little sculpture, and this was with your, I believe, parent company of the sponsor, and Shishijam, did I say that right? Okay. I've been calling it Sissikam for 10 years, but anyway, you told me today it's Shishijam, I think. And the architect Yushel, who is here today, and it's very nice to see him again. And just a funny story about this structure. I don't even know if I told Yushel this, but this was a deal, you know. He said, okay, you've got to design the structure within a certain time, because if you don't, we're going to penalize you financially. You know, I thought, we don't normally get that sort of restriction. And so on the way back from Turkey to my office, I was doing the design, and I did the design, really. I did it, you know, on the back of an envelope sort of a thing. Actually, it wasn't, it was 4 pages. And I gave it to my engineer in the office, and I had to go away for 2 weeks somewhere. And I said, just get it done because it needs to be done for when I get back. Okay, so I got back. I said, how's it going? He said, oh, it doesn't work. That's my engineer. And I'd given him all the calculations, and Yushel, I'm hearing these voices saying, if you don't have that by it, you'll have to, you know. So I'm thinking, oh my God. So we had 3 days, myself and another engineer, and we sat down and we sorted it, and we did it, we got it done, and we got it out in time. And this engineer who'd said it didn't work, I'd invited him to the exhibition, which was in Germany. And, you know, we were walking by, and they built it, you know, it was actually in the exhibition. I said, well, what do you think, Ian? You know, what do you think of the... He said, no, it doesn't work. Well, and what was really nice was when I came here in 2011, I met Yushel, and he said, I want to take you to see your sculpture, and here it is. It's been there since then, and so I must take my engineer to see it. Anyway, and these are projects we've been working on with ERA, who was a sponsor, I think, at the 2 years ago, Park Pond's sponsor. So we've been having great fun working on glass and facades, and even one on China with them. Anyway, these are the inventions, and this is the very first one. And I show this picture because it actually demonstrates one of the curious things about the glass industry, which we as consulting engineers can't afford to be light-hearted about. Right? Now, this is a very funny picture, okay? And it's demonstrating the strength of toughened glass. This is toughened glass, okay? Now, toughened glass, it's even, I mean, it is described as safety glass, and it's described as safety glass because, as was said before, when it breaks into small, 2 speakers before, when it breaks into small pieces, they're not so harmless, you know. Just to illustrate, well, number one, what happens when it breaks? What happens when it breaks? Okay, those ladies wouldn't be happy. The second thing is, Waterloo Station in London had toughened glass panels on the roof. They weren't laminated, just single glass panels. Now, what happens when they break is that, yes, Yes, there are small fragments, but due to Galileo's law, they all come down together, you know. And if you're underneath it, you don't want to be, okay? You don't want to be. So what happens when it breaks, whether it's toughened glass or heat-strengthened glass or annealed glass, is a very important question, and we must ask it every time. And even, you know, the toughened glass used in, and it still is, in vertical windows in buildings, there was a phenomena which involves basically an ingredient that's in the glass matrix, nickel sulfide, which the industry was struggling to come to terms with, because when you toughen glass, this nickel sulfide can become an agent to its own destruction, and you can't see it. It's sort of hidden in there. And it first started, or was brought to the public's notice in Australia, because there was a lot of windows in this tall building that were going bang, and when they went bang, they were falling on the pavement. Well, if you're in a country where you can sue somebody for, you know, almost anything, then you get worried. So I think one has to be very careful about describing glass as safety glass. This staircase is very safe. This is the glass company's steel angle with a sheet of glass. It's a very simple design. It works beautifully. If the glass cracks, it is so thick that it's not a problem, really, mostly. I mean, you could argue that you might get a flake off the bottom, but to be quite honest, it's a pretty robust design. But as I mentioned, my architect doesn't like the steel frame. He likes this. Okay, so this is designed with our very primitive knowledge of tensile strength of glass, and it's a piece of glass, and it's sitting on a piece of acrylic. So what happens when it breaks is the acrylic supports the glass. It's very simple. It works very well, and this particular architect has used it on every single staircase since we first invented it, which was 1989. And this is it, and this is the one that we were all saying, you know, no one will walk on it. Well, it's in a shop. It's in a fashion shop. And funnily enough, nobody seemed to mind. They were going up and down, off they went. This architect is what I call in the Baroque school, so she likes everything to be very, very detailed and designed, and all the metalwork needs to be very carefully designed. Because you see it in glass structure. You always see the connection. So lots of staircases with her, which are always fun, you know, they're sculpture. They're really sculpture. But always the same principles. Now, we moved a step forward, not a big step, but a step forward, when we designed these panels for outside. And in this case, we used two pieces of glass laminated together. Well, it's absolute currency now, but it wasn't then. So, and again, we designed it on the basis of 10 MPa. Was there tensile stress, 10 MPa? Two sheets, one breaks, the other one's still there. Annealed glass, because its crack pattern is more beneficial than toughened glass. Toughened glass, when it's gone, it's gone. There's nothing from it. It gives you nothing. It gives you everything when it's there, but nothing when it's not. Okay, so heat-strengthened glass, which breaks like annealed glass, is a good compromise between the two. But a lot of our designs were annealed glass, including this design here. This was the first glass beam and glass column, tiny little project, but it made a big splash, made a big impact on the design world. This is what I'm talking about with that wonderful work by the architect who spoke earlier. It ripples out much further than you can imagine. You know, you think you're working intensely in your own little world, This job took us to Japan, there's no question, and then to America. And we weren't a big practice, we were small. And this is what took us there. The reason? No one had ever done it before. Why not? Well, because there's too much risk, okay? And, you know, we actually wrote to the biggest glass company that we could think on. We wrote to them. Well, it wasn't Jishikam. I'm sure they would have had a very different response. But the one that we wrote to, they wrote us a letter back saying, under no circumstances should you build a structure. We were brave. We weren't brave. We were sort of halfway through the process. We were absolutely... but you know, once we built it and you could feel it, you sort of thought, actually, it's fine. You know, it's absolutely fine. And all our calculations and numbers are fine. This is very advanced, actually, because it's even got glass spacers. This is 1991 or something. It's got glass spacers, and it's got a sputtered on heating element, so there's no radiators in the room either. Which this is the architect who likes, opposite to Baroque, he liked everything with no detail. And someone mentioned earlier, the first speaker, about glass on historic structures, that this was glass on a building where it was historic, and so they said they couldn't identify the style, so they basically said it gets permission. The detailing was all, at one level, very crude, but at another level led to slightly bigger, more sophisticated solution. These are 6-meter beams, but basically the same invention of laminated beams, laminated columns. What happens if it breaks? We have 3 beams. If one breaks, we have 2 beams. If 3 breaks, we have no beams. But we have this magical laminated material, this stuff which is sticking the glass together. So they all work together and provide a nice fail-safe scenario. Now, glass beams and columns connected with friction grip bolts. I'm sorry I can't speak to you in Turkish, it's terrible. I'd love to do that one day, maybe. But friction grip bolts are used for basically joining toughened pieces of glass together and used in glass fins. But we used it in glass beams, and in this case we laminated the glass beams, so we had to develop a very particular solution where we put aluminium in here in this joint so that the compression didn't get lost, the friction didn't get lost when we tightened this up. This is our testing engineer. The engineer must not fall through glass roof, and then he can come home. Very simple design, and this was a real engineering development, which was for a project in Tokyo, okay? Now this definitely came from the small glass project. You know, they saw that and they thought we could do this. And they said they wanted, this is Tokyo, you have earthquakes, I know, but they have bigger ones, right? I think. They certainly have big ones. And they also have typhoons, so it's a big challenge. In fact, it was again a little bit like the glass staircase question. I felt like saying, this is the wrong place for a glass canopy. You don't really want to do a glass canopy, do you? To which they said, yes, we do. So, okay. So I came up with an idea which was, you know, it's 9.5 meters, and I knew I couldn't then, this is 1995, I couldn't get a piece of glass toughened, because I knew it would need to be toughened here, toughened laminated that was that long. So I thought, okay, maybe I can bolt two pieces together. And this is where the small industry, the small maker can help, because he made this little model for me of the bolted connection, and we did a very crude test inside these two channels. These are the bolts here. The glass is in the middle there, and we're pushing down here like a lever, like that, and we're getting a load in the bolt of 6 tons. 6 tons in the bolt. It was toughened, 15 millimeters thick, 6 tons. So we went to see the client in Tokyo with an answer, and it's always good to take a model, and this is a model showing how the structure works. So cantilevers, bolted, so it takes the load off the bolt. If they're stuck together like this, you get very high loads, but if you overlap it, it reduces them. So you get this nesting of the beams, and they then, the Japanese industry, and I'll just say this, we don't do it, but I think it's a wonderful idea, that the Japanese have 5 big contractors in the country. And every year, they get together and they discuss who they will support during that year to develop architectural design ideas. And they do something like, maybe Toyo Ito, this Museum of Columns. I know that the building cost 5 times more than a building of equivalent scale, not a research building. And he researched welding, he researched all sorts of cladding types, very clever. And then they distribute the information to the whole industry, so they don't sort of lose it in one project. So this is the beam that they made for testing, and this is the test, and this bolt here, in here, holds it there. There's another bolt holding it there, and then you push down on this side here. And they were pushing and pushing and pushing, and bang, went bang. And we went across, and the bolt had gone, choom, and the glass was still okay. First time. Okay, so the glass was stronger than the bolt. So we then got a stronger bolt, and put the stronger bolt in, and did it again, and it broke at 12 tons. That's a lot of load, which we were quite happy with, because in our design we'd allowed 1 ton, only 1 ton. So we had a factor of safety of 10. And this is it being constructed, the Japanese team here. This is them putting it together. And these bolts are 50 millimeters diameter. This glass is 2 pieces of 19 millimeter laminated, and this is also 2 pieces of 19 millimeter laminated. So there's a lot of fail-safe, And this is the structure, and this is the elevation. Now we continued that philosophy into the Tickets Pavilion in Times Square, which is a set of red steps which you can sit on and eat your sandwiches and watch the theatre of Times Square. So it's a very quiet spot in a very noisy place. And it was won by a small Australian architect, and he wanted to do glass steps, and he wanted to have it as transparent as possible. So we designed, with the same principle, these are glass beams. They don't look very glassy, but they're glass beams. And there they are there. Unfortunately, we had to put a gutter in, which was a bit of a wrong design decision, but that's the tread profile. And this is the mock-up showing the tread, which is in red, the riser. And then these are the glass elements. And they were overlapped as well and bolted, and that's how it was made. Now I'm going to go back to this project because one of the other inventions here, was simply the idea of stacking glass. I mean, nearly always you hang glass because you think that if you stack it, it would buckle, you think. But it doesn't. It's actually fine. And we're stacking the glass here, so this piece sits on top of that one, and that piece sits on top of that one. And it's all just silicone back to the structure behind. So it's a very, very simple design. This is also stacked, right? All of those, that piece of glass is stacked on that one, on that one, on that one, on that one, on that one, on that one. And you might say, quite reasonably, what happens when that one breaks? And what happens when that one breaks is it will probably stay in place because it's laminated, first of all. But secondly, that silicone joint up there will support that piece until you replace it, because silicone's very strong. Then we actually did it to support a steel roof, which always looks a little bit more dramatic. They wanted a completely glass wall because of this rather nice view. So this is them putting the wall together. It's completely flat, and we had a special arrangement at the top to spread the load out between the glass panels, but they're directly supporting the roof. Each of these pieces of glass directly supports the weight from the steel, and that's why he wanted it, really. I mean, again, it's this architectural thing, you know. I mean, if you ask me, I'd put a column in the corner. And why not? Well, it would save a lot of money, wouldn't it? And I'm Scottish, so I would want to do that, you know. But you can see, you know, that there are architectural dreams which, even if I don't understand them, I like to help to realize them. Sometimes I do understand them. Sometimes when I see them, then I understand them. So sometimes it's an act of faith, but one I've always participated in. Now, with the same project on tickets, this end wall here is actually holding these beams which are spanning 10 meters. Okay, they're spanning 10 meters, they're bolted into the wall, and they're 4 meters high. So they're just flat pieces of laminated glass supporting the whole of those steps going down. But when you test it, I mean, it's amazing, really. But we took a piece of glass, only about this size, just to test what would it take to crush it, not buckle it. I mean, buckling it, you know, it buckles easily. You understand that. You know, once it buckles, you tension here, so you know when it's going to break. But you think, okay, if it's really short and I'm really pushing it together, what sort of force does it take till it breaks? Now, it was no bigger than this computer screen, and it went up to 168 tons. 168 tons. We actually broke it, and it broke right down the middle of the piece of glass. Longy ways, like that. So, it's, you know, we're kind of nervous about what happens when it breaks or what happens when it gets a crack. And you know, one of the things which I'm hoping that we can educate the general public with is the idea that it's okay to have a crack in your glass. It's okay. If it's been designed such that what happens if it breaks been thought through. And I have to say that walking around the mosque yesterday, the Soleimani Mosque, every floor tile was cracked, and there was nobody replacing them. Why not? Because you know it's all right. Is it offensive? Not really. It's history. So maybe one day, it probably won't be in my lifetime, but one day you might look at the crack in the 18-meter long piece of glass and say, nah, I don't think we'll replace that, you know. Because one of the big things about glass, when it gets bigger, is that it's pretty expensive. Pretty expensive to put a new one in. Sometimes even impossible, because you're going to build it into the building. And there is another strategy, which is to say, okay, it's broken, but okay, there's 5 pieces, who's worried? It's only one. Maybe that'll take part in our thinking. This is the first Apple store in New York, and this is also glass wall panels with fins supporting the weight of the staircase, so it's a bit clearer there. You can see the wall panels there, cantilevered out of the ground. And then even used on an airport control tower where they wanted to see all the way around. And they didn't want any mullions, and they didn't want any columns. So this was the answer. Glass again. Isn't it amazing stuff? And this, I hope, will just about be built now in Philadelphia. These sheets of glass are 6 meters high. 6 meters high, and they're cantilevering from here. So it's 2 cantilevers holding the roof panels, which are also 16 meters. Now this is the big project I mentioned, which was the one at 60 meters diameter across here. And these are the cables supporting single sheets of glass, laminated glass, over maximum of 30 meter high. That's the whole building on plan. And there's the diagram. Now, what we did here, which was a different thing, the innovative thing, was that we tensioned the cables with weights. Now, how dumb is that? It's like so simple, you couldn't believe it. Most cable walls, they've got very sophisticated springs, and you have to go and tension them again, and the building moves, and, you know. This is the simplest thing you could imagine. But the industry had not seen it before, and to be quite honest, if I'm a contractor and I'm asked to do something I've never done before, and I've never seen before, I go risk, risk, risk, dollars, dollars, dollars. Risk, risk. So how can we remove that risk? And I want to emphasize it again. We can remove that risk if you hire me, okay? The consulting engineer, that is his role, and has always been his role, believe it or not. It goes right back to concrete and steel, because when those materials were first introduced to the world, guess what? They didn't have architects in mind. They were run by engineers, and we did the factory stuff. You know, we built steel factories or railways. It wasn't architecture. It was functional, good, solid, economic stuff. Okay, and we do the same thing time and time again. And we patented everything. Okay, everything was patented, protected. It's our design. So did things move forward? No. So the architect's looking at all this stuff, and he's thinking, that looks like the future. So he goes to the industry and he says, excuse me, can you help me with my funny building? And the engineer goes, no chance. Would you like this one or that one? Now, I'm not saying the glass industry is like that. It's not. It's much more sophisticated. But ultimately, it has to be, because its interests are different. It's about bottom line, and it's about doing as much as possible of what you did yesterday tomorrow, because that's where your profit is. Okay, if I'm in an industry, that's what I'm doing. Forget the design stuff. I might do something to keep ahead of the game, but I'm certainly not going to do something that means I have to hire a different set of people, change the machine, and, you know, I don't want to do that. So invention or innovation can only happen if someone takes responsibility. And in the glass, in the concrete and steel industry, what happened was the architect very cleverly pulled the engineer out of industry, and he put on a suit and tie, sat him down, and he did calculations. So that at the end of the design period, he said to the contractor, build that. And the contractor said, well, how do I know it's safe? How do I know it's safe? And the engineer said, because I said so. And that's the difference. That is the only difference, but it's a really critical and important difference. And I never would have understood it had I not worked on these glass projects. And this was a prime example. The contractor would not move forward with this design because he didn't understand it, even though I understood it. And then it took me to say, oh, I see. I take responsibility, and you can build it. Oh, yes, okay. And that's what happened. And not only that, but you then open the field to a much broader range of people. Because those with the design capability, or maybe, the Seeleys of the world, or the Wagner Bureaus, or, all those people who are very good at what they do, have their own design shops, you see. And if you want something clever done, you've got to go to them. You can't go to the glass guy down the road, that was doing the architectural stuff earlier that we saw. You've got to go to these big guys. But you can release that with the engineers, okay? The engineers, you've got to get them to take responsibility for the glass, though. It's a growing number, but when I started, there was only 2 of us that I knew. One in Holland, one in me, in England. Now there's many people, and it's spreading. So if you're an engineer in the audience, it is another thing that we should be offering architects. And the codes are coming. The codes will eventually come. So this is based on the design that basically the cable deflects when the wind blows, and the weight simply goes up and down. And that's the diagram of the. That's the wall being built. You can see, very simple. Cables hung from the arch, glass stuck onto these corner brackets, and that's the corner bracket, which is cast stainless steel, but there's lots of them, so it was very cheap. And that's the connection. Now this was like 1998, and the cost was $100 a square foot. So I don't know what that means to any of you here, but that's what it cost. The people who were going to do the alternative were going to charge $250 a square foot for a design that we didn't want. These are the weights which are attached to the bottom of the cables. And this shows the transparency that the architect was trying to achieve here. And of course, once you start, once you do the first one, then everybody in industry can suddenly do it. There's suddenly you have 5 contractors. Yeah, we can do that, we can do that. So, but you need to do the first one, okay? And so this was one we did at Princeton. With vertical cables, you can go around corners, which is quite nice. And this is another going round corners version of the same thing. There's the cables, and there's the glass stacked one on top of the other elements. And this is a version of the cable wall with horizontally pulling down on that lever which tensions the horizontal cable. This is the one where the glass is stacked. So it's all just sitting on each other, and the cable is stopping it kicking sideways, but the cable is always with the same tension because of this constant movement. This moves up and down. In fact, what was nice was the client realized that these would move up and down in the wind, and so he asked for them to be exposed, and he put the insignia of Indianapolis on here, so that you see these big medallions going up and down in the wind. This is another curious but I think, interesting way to build glass structures, which is instead of having glass going from there to there, which might be 10 meters, you can actually break it up into smaller pieces. It's called reciprocal beam theory, and each small section of beam is not continuous. So that one stops there, and that one goes to there and stops there, and that one stops there. It looks like it shouldn't stand up, but if you try it, even with sort of 4 knives, you can do it. You can stand 4 glasses, 4 knives, and you can stand the glass in the middle. And it's a good way to work with glass because the detailing's much easier. So this was what we did on the Apple store in New York. You can see it's like a joist hanger, this. We call it a joist hanger. Simply supported onto here. That one goes to the next one, etc. Now, flexibility, glass and flexibility. We heard earlier. The funny thing is, it is actually very flexible as glass. It's more flexible than steel, 3 times more flexible than steel. And can we use that? Well, this is a job in London in the Victoria and Albert Museum where the roof is sitting on glass beams. And each of these glass panels, it's a different shape and it's needing to go round a corner. Now what happens when you go around the corner is that the beams were different lengths. So one was that length and then another one might be that length. So if you're putting a piece of glass that's sitting on this beam here, here, here and here, it's actually twisted. Now we knew when we were designing it that it would be a little bit twisted. Yeah, it's fine. And it was one of those things, we got to the detail design and we're doing the drawings. And then someone said, do you realize that it's going to be twisting 150 millimeters? I said, what? 150? We thought that's too much. So we sort of looked at it, did the arithmetic. You know, basically it's like holding 3 corners in the one position and then pushing the other one down by 150. And we checked the glass, and it actually worked out that the glass was okay. Stress in the glass was okay. And the only concern then became, because they're insulated glass units, was that along the edge, that the edge spacer might get, you know, outside the warranty for the guy who made the units. So we asked if we could test a piece, which we did. So this is the piece being tested. And what we found, which is a nice result, is firstly, it only took one person's weight to bring the glass into position, which is important when you're installing it. And the second thing, well, that's the glass, and that's simply cold bent. Okay, the glass was completely flat to start with, and you would just stand on the end, and down it goes. And the stresses on the glass are absolutely fine, but what was very nice is that the edge is not curved that we thought it would be, it's actually straight. And that's a real surprise because we thought it would naturally be curved. But there's only a very slight curve on it, and that's because it's a hyperbolic paraboloid, just for any mathematicians and answers. And it allowed us to complete that roof much more economically than if we'd had to hot bend the glass. It would have cost a fortune. Now back to the Apple stairs, because this tread was the first time that we could confidently say we could put a piece of glass laminated from edge to edge without front and back supports and stand on it and be happy that when all the glass broke that I'm still here, you know, because 2 pieces of glass can break. You know, it's all very well having something laminated, but you've got to have more fail-safe. So we discovered with this new laminate material called Sentry Glass, which is an ionoplast material, that you can actually, with 4 pieces of glass, which we have here, you can do two things. One is you can bind all the glass together, and secondly, you can even laminate into the glass the metal connection. And you can break all of the glass, and it will still be there. It'll still be there. And that is really, really a big jump forward, because I think I can now honestly say that there is really no structure, virtually, that is beyond the use of glass. I mean, it's quite amazing, but I mean, you obviously wouldn't want to build a 10-story building out of glass, he says optimistically. But the architect, no doubt, will come one day and say, excuse me, do you know how we can build a 10-story building? So off we'll go again. But you really can do a lot that you could never do before. I mean, it's still flat. It's still expensive, not cheap. And therefore you, I think, want to use it sparingly, considerately, and, you know, in a composition that uses it in its best way for the light, for the transparency sometimes. You know, all of these things are wonderful attributes of glass. But I think the greatest challenge to us is the one that everyone understands to be the challenge, which is how do you keep the building hot, how do you keep it cold, how do you keep the light coming in when you want it and not. But I'll tell you, it's a lot easier to experiment with those choices if you start with a glass building and then try and mask out the other ways. Then if you start with a solid building, then you can't do it. So glass has that wonderful aspect that if you could afford to build a completely glass structure, box, everything glass, you then should have the potential to do all of the things you want to do in terms of environment. Letting, you know, doors that open and shut, blinds that come down and up. And of course, the industry itself is doing all of that exercise at the microscopic level. The low E coatings and all these high sunstream coatings are absolutely great. The other nice thing that no one has yet done properly yet, but I think it's the most exquisite thing, is the vacuum glass. Okay, we know it's been around and it's been talked about, but someone pointed out to me that if you extract the air from between two pieces of glass, you are removing 1 atmosphere of pressure. Okay, what does that mean? When they told me that when I pump up my bicycle tire, I put 6 atmospheres of pressure in my tire. I'm quite happy to cycle along and pump it up every now and again. Why don't we do that with the windows? Where that's so kind of energy efficient, you know, because there's no clever coatings around. It's just like 2 bits of glass and a vacuum, and you've got a U value of 0.4, 0.5, and it's only that thick. It's an idea that's coming for sure. You know, I can see that, you know, it would be like you just have a vacuum system with a pump around it, and you just maybe pumps away there sometimes and sucks a little bit of air out, and if it fails, you know, it's not a disaster. You just replace the gasket or something. Don't take it as a big sort of scientific thing. Take it at a craftsman almost kind of level. Could I do that? It's empowerment is the other thing that I wanted to say. Empowerment. Feel empowered. If the only thing you can choose are products which you can't... Have you ever tried to open up a modern car? The bonnet, I mean, you know, open up the bonnet. When I had my first car, I used to be able to open the bonnet, climb inside and fix the engine. Okay, now you open up the bonnet and it's, I wouldn't know where to start. And the car industry unfortunately likes it that way. They don't want me to fiddle around, really. But it therefore means I kind of lose both interest and inspiration you know, because when you're fiddling around, something comes together. So, you know, to be empowered to think and to do is to do things like that architectural suite of things we saw earlier, is to find the people who can do it and to be prepared to put your money where your mouth is. And yeah, you know, I was speaking to the architect and he was saying, you know, it didn't cost him nothing to do that. It cost him time. He had to invest a lot of his time in that. And I would also say to our clients, if there are any in the audience at all, money spent on the design period, no one can really fully prove it to you, but the number of times I've seen it saves you in spades, okay? So spend the money on your architect. Don't be mean at that phase of the thing, because it does more than just fix your project. It actually puts your culture, your architectural body on the world map. And unless you're going to invest in that, then you'll just drift back into being colonized by other technologies. You don't want to do that. It's not fun. It's disempowering. It's politically, as the first woman says, undemocratic, unlike glass, which is totally democratic. So these are more Apple things. This is, I think, a nice cantilever version of the same glass, so you can even cantilever the stuff. And this is where you bond the glass to the metals, so this staircase. This is the V&A project with a bent glass on the roof, but these panels of balustrade glass are actually bonded to a metal stringer plate. There you see, stainless steel plate. So no fixings, you see no fixings. It's a very architecturally clean answer. And speaking about politics, this is a project that somehow I got involved with in a fellow country of yours, which is Azerbaijan. And because of this wonderful lack of understanding, the person who called me from Azerbaijan didn't know what I did for a living, really. He knew I worked in glass, but didn't really know what I did for a living. So he ended up asking me to design a sculpture. So here it is. This is my first sculpture, which we also constructed. We actually got our hands dirty and worked with the steel guy. It's quite big. It's like, I was looking at those minarets at the Suleimani Mosque, and they're about 50 meters high. This is about 30. So it's quite big, about 4 meters on the bottom. And it's got glass bars which go from side to side as the thing twists up, you know. And they're held in these metal containers. That's looking up a stainless steel leg, which is kind of polished. And that's the bars, made in China. And this is the bar test. That's the other thing, you see. This is empowerment. This is empowerment. If I took this to university, they would say, whoa, cool, that'll be a sort of 2-year Master of Science program for one of our students to find out the strength. I don't want to know that. I just want to know if I do that, does it break? With a big factor of safety, okay? I understand the environment affects it and all this stuff, but I need to know whether it breaks at 3 times the load or 5 times the load. As long as it's not sort of 1.1 times the load, then I start to worry, okay? I even start to worry at 2, to be honest. But this gave us the confidence. Wonderful Chinese invention of sticking the 4-meter long glass things in rainwater pipes and then wrapping them. So 760 bars arrived in Afghanistan, and not one was broken. And not one was the wrong size. That was a miracle. And that's the thing built. And it lights up at night, of course. Da-dun, da-dun. You know, you get this sort of national anthem and lots of water. But it was great working for a president who was, let's say, unbending in his desire to have something by a particular date. In fact, I was sure we were going to get murdered if we hadn't finished in time. You know, it was a sort of, they were getting angrier and angrier as we approached D-Day, but we did finish it on time, and it was great fun. And we're trying to persuade them to build this just now. They've not got around to it yet. I think they found out I'm not really a sculptor, but anyway, who knows. But we proposed this, which is to build a sphere, but to build it out of flat pieces of glass. That's a lot, you know, because it's 25 meters diameter. So if you divide by 25 by 25,000 by 20, it tells you how many layers there are. A lot of layers, but. And the idea is just to, sorry, pressing the wrong button, is to cut the glass. You see, if you cut it and then cut a wee bit out of it, you can build up the pattern. So you get this really kind of wonderful Islamic egg or something. And hopefully they'll commission me, because that's my pension, but there we go. Okay, thank you very much.
I have a few questions.
Another question.
Evet, Tim'e sorusu olan var mı acaba? Sanıyoruz yok.
Okay.
But may I please ask you to stay on stage for a while? Değerli konuklarımız, tekrar çok teşekkür ediyoruz bu konferansımızda bizleri yalnız bırakmadığınız için. Şimdi izninizle değerli konuşmacılarımız Ayşe Solerktin ve Ahmet Alıtaş'ı sahneye davet etmeden önce bir soru geldi oradan. Çok özür diliyorum. Bir saniye tabii ki olacak. He's gonna ask a question in Turkish.
Oh, okay.
Özellikle Apple Store'da kullandığınız camlar bizim bildiğimiz temperli cam şeklinde olan mı, yoksa alaşımları farklı mı? Yani kullandığınız materyaller farklı mı? Taşıyıcı özelliği, dayanım miktarı, kilosu vesaire farklı mı? Şöyle söyleyeyim. Tasarımlarınızda kullandığınız
No.
Why don't you say it to me?
No. What's up?
Bir söyler misiniz?
tasarımlarınızda kullandığınız
Said it now?
Yes.
Okay, sorry. Yes, I can hear you now. Yeah.
tasarımlarınızda kullandığınız camlar, hususen camları söylüyorum, glass. Bu camlar bizim bildiğimiz temperli şişe camında ürettiği temperli camlardan mı, yoksa farklı bir cam mı? Yani alaşımı farklı bir cam mı? Evet. Bir de
You just tell me what you said.
Çok pardon, teknik bir sıkıntı galiba. I think there's this technical
Turkish.
yeah, he's just basically asking what kind of glass you used in Apple Store.
An Apple store was
Yeah.
Yeah.
Farklı. Yani neticede kendi kullandığınız malzemeler bizim ülkemizde de var mı, yoksa
The materials that you used in Apple Store and the other projects,
Yeah.
are they also available in Turkey, or where did you use that glass, or where did you bring that glass to your projects?
Did you say was it?
And, yeah.
The glass is it's laminated glass. Four pieces of laminated glass, and the glass is annealed glass, not tempered, not heat strengthened, annealed. Do you understand?
It's laminated.
It's laminated, yeah. The glass is laminated. Oh.
Glass was different early on, whether it's a regular float glass or not.
No, the glass was.
Önemli bir şey daha soracağım size. O camların bazılarını konsol şeklinde, kiriş şeklinde kullanmışsınız. O kirişleri birbiriyle entegre etmişsiniz, ama orada şey yok. metal kullanmamışsınız. Yani stainless steel falan kullanmamışsınız. Paslanmaz çelik falan kullanmamışsınız. Sanki camı birbirine yapıştırmışsınız gibi. Yani birbirine bindirerek taşıtmışsınız ama orada camı kilitleme sistemi de yapmamışsınız. Farklı bir şey yapmışsınız. Zannediyorum yapıştırıcı tarz, yani kimyasal, chemical tarzı bir şey kullanmışsınız. Onun ne olduğunu anlamaya çalışıyorum. Acaba ne? Yani DuPont'un ürettiği bir ürün mü var ya siz icat mı yaptınız? Nereden aldınız onları?
No. The bonding material is simply PVB. Each.
Tamam. Yani PVV var, okey, ama orada silikonize farklı bir yapıştırıcı daha var.
Yes, there's
Özel
silicone.
bir şey, sıvı, evet.
Of course, yes. Where the glass panel sits on the glass beam, there is silicone at the joint. Yeah.
Bizim bildiğimiz nötr silikon değil herhalde, özel bir şey o. Çünkü taşımaz yoksa. Yani bizde yok o. Siz
The weight of the glass
evet.
is carried on a spacer.
Evet.
And then the silicone is between the spacer.
Onu biliyorum, silikon, ama silikonun şeyi ne, içeriği nedir? Yani markası nedir ya da nasıl bir silikon? İçinde ne var silikonun?
It was a very early. Can't remember the number now, but it wasn't structural. It wasn't structural silicone. No,
Tamam.
it was weathering silicone, which Dow Corning have a number for, which I think is 763 or something.
Evet.
Çok özür diliyorum, zamanımız kısıtlı olduğu için kokteylimiz olacak. Orada sorunuzu devam ettirebilirseniz çok memnun oluruz.
Yeah, good idea.